in 100 ml. And so we want to convert that so the first one to do is convert that into moles per litre, because that's what we're raising concentration in. And at the moment, we've got both the wrong units, milligrams, and we've got the wrong volume. So if we times by 10, we end up with the number of milligrams in a litre. So at least the volume is right. And we can then convert milligrams to grams by dividing by 1,000. And that will give us grams per litre, which is a good starting point. If I go, so once we've got grams per litre, we can go from grams per litre to moles per litre by dividing by the molecular weight. 165.19. No, that's not 1.05 divided by 9. That gives me 0.003068 moles per litre, which is our concentration, I think. So once we've got that, we can type that. Let's go. So that is our concentration, C. So absorbance equals C times the extinction coefficient, which is C multiplied by 6,220, which gives us an absorbance of 1.88. So this effectively tells us that if we could somehow miraculously convert phenylalanine directly into NADH, the NADH number of moles per litre of NADH produced would give us an absorbance of 1.88. And we want the maximum absorbance to be nearer 1. And so this is effectively twice as high as we need it to be. So if we diluted it in half, we'd end up with a 0.94 absorbance units, which is close enough to 1 for our purposes. Now, of course, we can't magically turn phenylalanine into NADH because we need to add the enzyme and NADH in the co-substrate in the buffer. And of course, when you add the enzyme and the NAD and the buffer, you're diluting the phenylalanine. But what this effectively tells us, is we need to dilute the phenylalanine by a factor of 2. And so, of our 200 microliters of reaction volume, we want 100 microliters, or 1 ml, to be the phenylalanine, or the sample. Okay, because if we make 100 microliters of the reaction volume our sample, and then we add 100 microliters of all the other stuff, we end up with a total volume of 200 microliters, in which the phenylalanine has been diluted by half. 100 microliters is ended up dissolved in the total volume of 200 microliters. And that means the highest absorbance possible will have dropped from 1.88 to 0.94. So all this part of the calculation does defines for us how much of the reaction volume we want to be made up by the sample, or the standard phenylalanine solution. Okay. Does that make sense? If I go back to here. So this tells us that of our 200 microliters, 100 microliters will be the sample. That's important because until we've defined that, we can't work out any of the other volumes. So question 2 is basically, given that the volume of the sample we use, microliters, so when we're going to use 100 microliters, what's the maximum number of moles of phenylalanine in the sample? Not concentration, but the actual physical number of molecules that need to be converted. This is important because you're going to need an equivalent number of moles of NAD. You never want the NAD co-substrate to be a limiting factor. If you've got 10 moles of phenylalanine to react, and you've only got 8 moles of NAD, you won't be able to react to the last 2 moles of phenylalanine because you'd have run out of NAD. So it's important to define how much of the reaction mixture volume is made up by the sample, because that defines the number of moles that are going to need to be reacted, and that therefore defines how much NAD and how much enzyme you need to add. Okay, as I say, one of my greatest failings in life is a belief in democracy. So we'll quickly create a poll. Okay, so I've created a poll which, if I could get it to behave, it says, next 2 questions, we've got 2 options. We can either do them in breakout rooms and send you back to your breakout rooms, or I can go through them here in this room in that same manner of going through the Word document and talking through how I would approach it. Which of these 2 options would you like? And I'll try and look surprised when no one likes breakout rooms. Oh, it's a better ratio than I've had in the past. I don't know what happens if it gets to 50-50. Okay, I think that's... Okay, so a 2-to-1 ratio. That's better than I've had in the past, put it that way. What if I like who... Okay. So... again, democracy is a terrible thing. We'll never catch on. But I think we're probably staying here for at least the next couple of questions. I might sling you back in for the last one just for annoyance more than anything else. Okay, so let's go to the next question then. So the next question basically says, if we assume therefore we're going to use 100 microliters of sample, and we know what the maximum concentration could be because we've worked that out already, how many moles do you need to convert? And because you need the same number of moles of NAD. So, now then, if we go here. So we're starting off here then. This is our concentration of phenylalanine. Okay, this is the maximum concentration. So we said it was 0.0000303, I'm going to call it, moles per liter. Okay, so the first thing I would do is do the simple thing. So I don't like mathematics because it makes my brain hurt. So if you've got 0.000303 moles per litre, you must have the same number, 0.000303 millimoles per milliliter. Yeah, if you divide both sides of that division by 1,000, go from moles to millimoles and litres to milliliters, the number stays the same. And we've got effectively 0.1 milliliter. Yeah, we're going to take 100 microliters or 0.1 milliliters. So we're going to have 0.0000303 millimoles per 100 microliters. That'll be a tenth of this one. Hello? Hang on. Why is someone unassigned to... Hang on a second, no, I forgot that. Who's dropped out somewhere?
My Zoom played up, so I have to reconnect.
Yeah, that's what it is. Okay. Forever. Okay. So, does that make sense? This is our concentration, maximum concentration of phenylalanine, because we worked it out up here. Convert that to millimoles per milliliter, and then millimoles per 100 microliters, which is a tenth. And then just because I don't like numbers with lots of zeros in, I'm going to convert them from millimoles to micromoles. And to go from millimoles to micromoles, you would times by 1,000. Which is 0.0303 micromoles per 1 mil. So this is the number of micromoles of phenylalanine you could maximally expect to find in your sample. So by definition, we're going to need 0.0303 micromoles of NAD as well. We never want NAD to become the limiting factor. So we have to have as much NAD as to be able to convert all the phenylalanine into phenylpyruvate before it runs out. Okay. So our NAD solution is 1 gram dissolved in 745 ml of water. So the first question is, what's 1 gram in terms of moles? So the molecular weight for NAD is 662.4 grams per mole. You can Google it. Google is your friend. So the number of moles is equal to 1 gram divided by 662.4, which as a number is probably horrible. Yeah. 0.00150966 moles dissolved in 745 litres. So a key important thing here is when whichever student is writing up the rationale for the design of the assay, this is the sort of thing you discuss, but it's always important to keep a track of the units for every step and what's changing between units. Because if you lose that, then you get lost very quickly. Okay, so we've got a number of moles and we've got dissolved in a large volume of water. We want to get to a certain number of micromoles. So to make it easier for my brain to understand, I've attempted to convert these moles into micromoles. To do that, of course, you would times by 1,000,000. Times by 1,000 to get from moles to millimoles, and times by 1,000 again to get from millimoles to micromoles. And we get to 1,509.66 micromoles in 745 millilitres. So now we know how many micromoles we have in total dissolved in that total volume of liquid. And we only want this number of micromoles, 0.03, so we don't need to lose 745 millilitres, which is probably a good thing. So let's work out how many micromoles we have in a milliliter. Of course, you divide by 745. So if you divide by 745, you get to 2.2 micromoles per milliliter. So every 1 milliliter of that NAD solution gives you 2.02 micromoles. And from there, you can work out how many micromoles you would have in a microliter. So, and of course, divide by 1,000 again. Because the microliter is 1,000 per millimole. And you end up with 0.02 micromoles per microliter. So again, that's the number we need. And that's the number we have in every microliter. And so the first thing to note, of course, is this number is smaller than this number. So we need more than 1 microliter. And you should be aware that the volume required is equal to effectively the number of moles needed divided by the number of moles per microliter. In which case, this is 0.0303 micromoles needed. We've got 0.0002 in a microliter. So, divided by 0.0002 means that we need to add 15 microliters of NAD solution. if we add the 50 microliters of NAD, we're effectively adding 0.303 micromoles. And so we're never going to run out of NAD before we've converted all the phenylalanine to phenylpyruvate. Okay, so far so happy? Okay, so far we've worked out how much sample we're going to add, and we've worked out how much NAD we need to add to be able to convert all that sample. Next question on my list of silly questions is, again, given that volume and how much phenylalanine, number of moles of phenylalanine to get, what volume of enzyme do we need to do it in 30 minutes? Okay, so we said we're going to allow the enzyme 30 minutes to convert all those moles of phenylalanine to phenylpyruvate. And we've got all these different weird things, which we'll come back to now. So, go back to this file. Okay, so with the enzyme then, we have 1.1 unit of enzyme dissolved in 1.5 milliliters or 1500 microliters, how I like to think about it, of water. Okay, and we know that 7 units of enzyme converts 1 micromole per minute. So, first of all, I work out is basically, if we've got 1.1 unit and it's dissolved in that volume, how much phenylalanine can the entirety of that volume convert? So the first thing is how much can 1 unit convert? If it takes 7 units to convert 1 micromole, then 1 unit must be able to convert 1/7 of a micromole. And 1 divided by 7 is 0.1426 micromoles per minute. If it takes 7 units to convert 1 micromole, then 1 micromole must be able to convert 1/7. If we know how many micromoles per minute 1 unit can convert, the 1.1 unit must be 1.1 times more. 4286, because it's going to be slightly more. So times 1 is 0.15714 micromoles per minute. So far so good? So the entirety of that 1.5 milliliters can convert that number of micromoles per minute. Now we're of course giving it 30 minutes, not 1 minute. So we'll times it by 30. And that means that we can do 4.7143, give or take, micromoles per 30 minutes per 1500 microliters of solution, of enzyme solution. So if we use the whole volume and use the whole time available to us, we can convert 4 micromoles or 4.7 micromoles. We only need to convert this number of micromoles. So this is our target, remember? Oops. So we only need to convert that number of micromoles of phenylalanine. So, if we know this, I would be tempted to work out how many micromoles per half hour you could convert per 1 microliter. So if we divide that value by 1500, because that enzyme is all dissolved in 1500 microliters, we get 0.00314 micromoles converted per 30-minute period per microliter of enzyme solution. so as we know that enzyme is equally distributed across those 1500 microliters, if we take 1 microliter out and stick it on a reaction mixture, we can convert that number of micromoles in half an hour. Okay, so 1 microliter isn't going to do it because this value is smaller than the maximum number of phenylalanine moles we have. So again, we take the number of micromoles we need to convert, divide it by the micromoles per microliter, and that gives us our volume. Which gives us 9.65 microliters, which I'm just going to roughly round to 10 microliters. Enzyme. Okay, so given the enzyme's activity, we can work out what volume, and given we know how many micromoles of phenylalanine maximally might exist in our sample, we can work out what volume of enzyme can be assured to convert those micromoles in time available. Okay. So far, our reaction mixture is 100 microliters of sample, or phenylalanine, 10 microliters of enzyme, 15 microliters of NAD, and we need to make it up to a total volume of 200 microliters. So we're going to fill the rest with buffer. So obviously we're going to add 75 microliters to make it up to 200 of our 750 millimolar glycine buffer. Glycine. This then becomes our reaction mixture. Now, we said before, glycine buffer in the final reaction mixture to stabilize the enzyme has to be greater than 200 millimolar. So, fourth question is basically, given the reaction mixture volumes, do we have a great enough buffer concentration to be able to allow that to happen? So what is the final buffer concentration in the reaction mixture? So the reaction mixture is 100 microliters of sample, 10 of enzyme, 15 of NAD, and 75 of buffer at a concentration of 750 millimolar. So what I'm going to do is put you back to the breakout rooms because it's good for you, I think. And what I want you to do in breakout rooms is discuss two things. One is try and work out the concentration of the buffer in the reaction mixture and work out if it's enough or whether we need to change it. And secondly, determine which part of the write-up you're going to individually consider doing. If you quickly just find the write-up document a second. If we share that, so as I say, the write-up is split into 3 sections. So the first section is a mainly written section. The person has to write an introduction to PKU and assay principles and reference that. You also have to write a methods protocol, and the methods which basically tells students how to do the practical. So you need to be aware of how to do the practical, and you also need to be aware of what to do with the 5 mg per 100 ml solution of phenylalanine to make up your standard curve and QC concentrations. So what do you want the students to physically do in the lab with that stock solution of phenylalanine to make standard curve points? And you also need to write 5 questions you would want students to answer on the subject or a related topic, plus model answers to those questions. The second section is effectively the data analysis section. So I'll put the example data for the standard curves, the QCs, and the patients up on Canvas. And then you need to provide standard curves with error bars, line equations, correlation coefficients, to calculate how accurate the QCs are and whether the assay is working or not. Calculate the levels determined in the patients and controls, and determine the diagnostic accuracy of assaying phenylalanine to diagnose PKU. And says all the information you need for this is in the PowerPoint. And then the first student basically has to write the rationale for this design of this experiment. So why 100 microliters of samples is the right volume, why you need 10 microliters of enzyme. Explain this process we've been talking through in a written manner. Okay, so at that point, if you can all disappear back into your various